Hello, geometry. Long time no see via video. Um, let's jump into it. We are looking at Unit 9, and we are dealing with solids, three-dimensional shapes, prisms, pyramids, cones, spheres, all these 3D things. And the gist of today's lesson is vocabulary. And because the definitions are already written for you here in the notes, I don't see too much of a point to dwell on each one individually when you can just kind of read it yourself, right? I mean, right? I mean, the definitions are pretty nice, but I want to focus on some of the big ones, okay? I want to focus on some of the big ones. And that would be base, lateral face, and cross-section. So, the base of a polyhedron, which is a fancy term for a three-dimensional shape. Okay, maybe we should discuss that, right? A three-dimensional shape is called a polyhedron, okay? The polygonal face that distinguishes one polyhedron from another is called the base, okay? So think of all the 3D shapes that you know, right? You've got boxes, you've got cubes, you've got pyramids, you've got cylinders, right? Like a can of soup. You've got all these different three-dimensional shapes. And take a look at page 2, right? Here's this shape, right? What is that? What is that? What is that? Look at all of these shapes. Well, what makes these polyhedrons the way they are? The base, right? The polygon face that distinguishes one polyhedron from another. Distinguishes. This polyhedron here looks different than this one here. Why? Because the base is circular, where the base here is rectangular. These, I mean, they all have this height to them, right? They all have a height to them, and they all have these faces, right? But this is a triangular base. This is a rectangular base. This is a pentagon base. So that base makes the entire shape look different. This looks different from this, all because there's a hexagon here, or a pentagon here, instead of a rectangle. Okay? So they look different because of the base. The base is this like one distinguishing figure. And then the lateral face is everything else, right? Do you see how there's a pentagon on the top and there's a pentagon on the bottom, and they're like connected to each other? You see how they're connected to each other? When you connect them, you're creating faces, lateral faces. There's one back here, there's one back there, there's one over here off to the side, there's one in front, and then there's one here off to the side. So there's 1, 2, 3, 4, 5 lateral faces. So this triangle is connected to this triangle, and when you connect them together, you're creating faces. This like slanted face, and the bottom face, and the face on the side, right? I hope you see what I'm seeing, right? That we can only do so much when it comes with drawings. But that's what's happening here. We have this circle connected to this circle. So the lateral faces are the faces that connect the bases, right? There's a base on top and bottom, and we connect them together with lateral faces. And then cross-section is a pretty big idea, because you can like splice this down the middle, and when you open a can of soup or like a Pringles can, you're going to still see a circle, right? You can splice this up as many ways as possible, and when you splice it up, each little splice is just another circle, right? You could almost imagine a cylinder as a bunch of circles stacked on top of each other, right? If you took a bunch of circular pieces of paper and stacked them, and you had enough paper, it looked like you have a cylinder, right? So those are the cross sections, each of those little slivers, right? If I take a bunch of pieces of paper and stack them on top of each other, right? Sort of like, you know, when you buy paper at the store, if you've ever bought paper for your printer, it basically looks like a prism. It looks like a box of paper, right? So each of those little slivers are called a cross-section. So I think those are the big ideas. All right, I rambled enough about these definitions. Let's classify these figures. A prism is something that has two bases that are congruent and parallel. So there's this triangle on top, and there's this triangle, I think I just said top. There's a triangle on bottom and a triangle on top, and we are connecting them, right? That is a triangular prism because two triangles are connected to each other, creating this three-dimensional shape. We call it a triangular prism. Okay? So this is a triangle on top and a triangle on bottom, and when we connect these triangles together, we create a triangular prism. This is a pentagon on top and a pentagon on bottom, and when we connect the two together, we're creating a pentagonal prism. The bases help determine the name. You identify the base and you kind of make up the name with the base. Okay? What else do we have here? We have a circle on top and a circle on bottom, and we connect them together. We call that a circular prism. No, we don't. We give it a special name, and that is a cylinder. Why does it deserve a special name? I don't know, because it does. Right? Life doesn't always have to make sense. We call it a cylinder. You could call it a circular prism, sort of, but it's not. It's a cylinder. Okay? This is a rectangle on bottom and a rectangle on top, and we connect the two together, right? All of those edges there, and we create a rectangular prism. Yes, it's commonly referred to as a box, but technically speaking, it is a rectangular prism. What do we call it when we have squares connecting each other? A cube. We don't call it a square prism. We call it a cube. Switching gears here, when we have one base and then all of the faces connect to a single point up top, we call it a pyramid. But you can have pyramids with bases other than triangles. This is a triangular pyramid because the base is a triangle. But this is a rectangular base. But all of these edges here are still connecting to a single point. So we call this a rectangular pyramid because they're connecting to one point. The base is what really defines the shape. This is a 1, 2, 3, 4, 5, 6-sided base. That's a hexagon connecting to one single point. So we call it a hexagonal pyramid. We call it a hexagonal pyramid. This is a square pyramid. And this is a triangular pyramid. And then what is this? A circular pyramid? Sort of. But we call it a cone. And what is this? This is a sphere that just deserves its own name. It's not really anything, right? It doesn't really fit anything that we've looked at here so far. Now, I've kind of saved this one till last, number 11, for a purpose. what is the base of this figure? What is the base of this figure? You might be tempted to say, well, you know what? Question pops up on screen. What is the base of this figure? What is the base of this figure? What I was about to say, you might be tempted to say that it's a rectangle. Because when you hear the word base, you sort of think, well, that's what it's sitting on, right? It sits on its base. Just because I tip this prism over, I knock it over, doesn't make it a different shape, right? It's still a pentagonal prism. And just because I, tip this over and knock it on its side doesn't make it a different shape, right? Just because it's sitting on a triangle doesn't make the base a triangle. And just because it's sitting on a rectangle doesn't mean that the base is a rectangle. It's about what defines the shape. So what is the defining characteristic of this shape? We have a triangle connected to a triangle. The base is a triangle. It's just a triangular prism that's been knocked over. There's a triangular prism that's been knocked over. And then this guy doesn't fit any of our molds. To be honest, I don't really know if it has a technical name besides a generic polyhedron. It's not really fitting any of our typical naming schemes. Polyhedron. It doesn't really fit any of our naming schemes. Why not? You might be like, well, isn't it sort of like a rectangular prism? You have a rectangle on top and bottom. Right, but they're not the same size. This rectangle on bottom is bigger. So it's sort of... Or whoa. I'm stupid. Whoa, my eyes deceived me. This is the same shape as this one. It's been knocked on its side, just like this one was. It's been knocked on its side, just like this one was. So we are connecting... Do you know what that shape is called? A trapezoid. So this is a trapezoidal prism. All right. Hopefully that was fun. I had a little fun. Let's jump to this last page. By no means are we going to do all of this. I'll probably save one or two for our Socrative. But let's look at the first one, I guess. So this is called a net. Now, this is very hard to describe digitally, let alone in real life. But imagine that a cube or a prism or a sphere or a cone or a whatever is hollow, right? And you snip it all along the sides and you open it up, right? You say, okay, I'm going to flatten this thing, right? Like, imagine taking an Amazon cardboard box and, like, breaking it down so that way it's one flat piece of connected cardboard. You could fold that back together and reform the box, couldn't you? Right? I mean, it was a box, right? And then you flattened it out. Well, what you created was a net of that box. You have flattened it into this two-dimensional shape, but you could always fold it back together. So that's what a net is. And it gives you a nice visual representation of the surface area. Surface area being, okay, if I find the area of each of the faces, then I can find the area of the surface, the visible surface, right? The stuff I can touch. So you may or may not be able to look at number one and know what shape that is. What shape is that if I were to fold it back together? It is a cube. It is a cube. Number one, all of these faces are square. All of these faces are square. So we can see that the base is square. And if we have a bunch of squares, then each cross section is going to be square. you know, don't let these words intimidate you too much, right? The cross section is just when you splice it up and you go phew, 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 right? I would have a whole bunch of squares. It is hard to see this fold together, but like this piece, right, is going to fold up, right? So now we're looking at it dead on. And then this piece is going to fold like that, right? And then this piece is going to fold up, and then that's going to fold over the top, and then, right, you see this coming together? I don't know. So what is the total surface area? Well, if each of these are 14 by 14, well, the area of one single square, 14 times 14, is 196. If each of them are 196, because they all have the same dimensions, they're all squares, there's 1, 2, 3, 4, 5, 6. So the total surface area, 196 times 6, is 1,176. Uh, 16 minutes. I really only asked the one question, right? Let me give you a hint and ask you one more question, and that's going to be, what is the shape of the base? The base of a prism, it's always two congruent shapes that are connected together. These two congruent trapezoids are connected to each other. These two congruent triangles are connected to each other. These two congruent pentagons are connected to each other. What is the base of this shape? There needs to be two congruent shapes that are connected to each other. What shape is that? Answer pops up on screen. This isn't too difficult of a question, because actually when you look at this, right? By the way, this might look like a square. It's not. It's 21 by 16, right? Don't let the visual fool you, right? This is 16. These are all rectangles. And this rectangle is the same as this one, because it's going to fold up, right? And this rectangle is the same as this one. Now, which rectangle is the official base? It doesn't matter. The point is that the base is a rectangle. It doesn't matter which one you declare the base. They're all rectangles. It's all rectangular, so the prism is a rectangular prism, no matter how you cut it, right? Like, it doesn't matter what you declare the base. The point is the base is a rectangle. So it's a rectangular prism. And what are the shapes of my cross sections? Holy cow, rectangles, right? So what is the total surface area? Last but not least, you can use these dimensions. So this is 7 by 16. So 7 times 16, length times width, right? Hope I'm not blowing your mind there. Length times width is 112. And so therefore that's 112. This is 21 by 16. So 21 by 16 is 336. So therefore this is 336. And then what are the dimensions of this box? Well, this piece and this piece are going to fold together and meet up, right? So this 7 is the same as that. 7, 7. And then this is 21. So 7 by 21 is 147. And when you add it all together, 147 plus 147 plus 336 plus 336 plus 112 plus 112. 1,190. And you know what? With that, I bid you adieu. If you struggled with the visuals here, hopefully staring at it a little bit more, maybe I can find a video or something like that for class. But hopefully you definitely feel comfortable with the naming and identifying shapes, and maybe the net will grow on you. Okay? I know that can be a little challenging to visualize it coming together. All right. Thanks for tuning in. I will catch you in class, and I'll see you in the next one.